Well, I suppose we'll get started. Um, so, like I sort of mentioned, I didn't realize this was a cohort that started in spring. Um, so the first little bits of this class are geared more towards introducing logical operators. I mean, we are going to take a math stab at it. It's not purely going to be programming, but the intent is to get students comfortable with that sort of thing before they start diving too deep into programming so that they're not lost in the sauce. Um, so some of it is going like already it's basically plain English for the logical operators and just being a little bit more formal. But you've definitely seen it a lot with working with Python. But just because I don't want to make any assumptions, I am going to just do what I normally do. So I'm sorry if it's a little basic. So with that said, I'll talk more about the important math thing, which is the quiz. So I haven't gone over the results yet, but I'll tell you that there's not going to be any surprises in it. It is kind of funny though that on day one I give like the course outline and I'm like, all right, here's the thing to make you feel bad about yourself, and then everyone's like, great, thanks, I feel bad about myself. Here you go. So that's kind of how it is. I do the quiz for me, so that I can get an idea of where everyone is, just in case. I'll say I've never had I've never had it happen where like everyone hands in the quiz and I'm like, wow, everyone is like factoring polynomials like it's nobody's business. Like that's just never happened. But it could. I got to make sure. But I do have little variances in the things that students struggle with. So an important thing about that quiz, I kind of mentioned it in passing, but maybe by that point everyone was already working on it. They weren't paying attention to what I was saying. We don't need a lot of that stuff. So if you're worried, if you're looking at it and you're like, there was factoring quadratics on this, I don't remember how to factor quadratics. That's okay. I don't think we need it. There's a couple things that we will need, but I will cover them as we need them. So this is the point of the quiz is for me to get an idea of how much do I need to go into detail on it, right? Like if everyone in the room seems to know how to do factor trees or factor numbers into primes, I'd be like, okay, well, I don't really need to talk too much about it. But if like most of the people in the room were like, I don't remember how to do this, then it's like, okay, well, I'll spend a bit more time reminding you how to do it. The other one is the last two questions, systems of equations. I see a broad spectrum of people write, I have no clue. And then I have people doing the solutions that that I'm going to present in linear algebra, right? So they're augmenting and row reducing a matrix, or they're doing determinants or whatever. If you don't know what that means, that's fine. But my point is, I've got a spread from I have no idea to I already know what you're going to teach me and I'm doing it right now. So the point is, I'm going to teach to I don't know, not I already know what I'm doing. And that's kind of the point for all of it, right? So like if I think I said it again in passing, I've had students who put I don't know to literally every question on that quiz, and they were being genuine. They weren't just being like lazy and saying I don't know just to get the 1 out of 1. They were like, I genuinely don't know. And then they were fine in the class. So, if you handed that in and you're like, I feel terrible about myself, it's fine. You'll be okay. As long as you just, when I say, hey, this is important and we're going to have a quiz on it, you're just like, okay, I'll write it down. With that said, I suppose we'll just jump straight into it. So we're going to start with an introduction to formal logic, symbolic logic, ultimately with the goal of you can sort of do algebra with logical operators, and that's really the goal is to be doing that algebra. Because I mean, yes, you've done a course on Python, but maybe you've never thought about how to simplify your logical statements, right? So you have a complex if statement with like a bunch of logical statements in there, like if this and this or this and this and that, and maybe you could simplify it by just thinking of how it works in a truth table style. That's kind of the point of what we're going to be talking about. So I'm sure you've taken a math class before, And in math, we like to make things formal and very strict on how we define things. Because actually, if you have any math knowledge, there's something called Russell's paradox, which is essentially stemming from the idea that if we just define a set as the naive way, as a collection of things, we actually end up with a paradox. So we're going to avoid that by being very formal. So a sentence or statement, we use them interchangeably, is something that has a formal true or false value. A definite truth value. Namely true or false. All right, so we've got either true or false. So it's easy to construct examples of this. An example is Travis teaches at Red Deer Polytechnic, which I hope you agree is a true statement and that I'm not some weird guy who just like walked into your classroom and said he was teaching you. So Travis teaches at RDP. We can assign a definite truth value to that, right? That is a true statement. Alternatively, Travis lives on the moon. Unfortunately, that is false. I do not live on the moon. I live in Red Deer. Right, so this is kind of the idea, right? True, we can assign truth values. Now, something that is not a sentence or statement not a statement is something that does not have a definite truth value. So I wrote this down in my class, and then it was like it wasn't divisive. It was like landslide. No one said yes. So I'll try it here again. Olives are delicious. Show of hands, who agrees with that statement? Okay, there's at least someone. Because when nobody says yes, then it's like, well, it's starting to look like something that has a defined truth value, doesn't it? In this case, there were people who said yes and lots of people who said no, right? So then that means we can't assign a truth value to that, right? It's subjective. It depends on who's answering it, right? So if we wanted to turn this into something that is a statement or sentence in the logical sense, so change this to have a truth value. Well, we can just make it more specific, right? So Travis thinks olives are delicious. True or false? I mean, I guess you have to ask me. I am a freak. I do like olives. Right? Woo, olives. But the point is now it has a definite truth value. You can ask me. You can say, Travis, do you think olives are delicious? Yes or no. Right? It is a yes or no statement, which means this is either true or false. Right? So these sort of subjective sentences in a language sense do not qualify as sentences or statements in the mathematical or logical sense, right? We want to be able to assign a definite truth value to them. But this isn't necessarily a bad thing in the sense of, a show of hands indicated there were a few people who think olives are delicious, but a bunch of people who don't, which means we want to be able to capture that as an idea, right? Of a variable or subjective answer that has a truth value depending on who's answering the question, right? And so we can capture that with something called a formula. So a formula is a statement, possibly with variables. So it doesn't have to have variables. Although it would be silly to not have them. Whose truth value, so whether it's true or false, depends on the value of those variables, value or choice. So this is very similar to the mathematical notion of a formula, right? We have some variables and you can choose those variables and stuff happens based on those variables. So it's no surprise then that the notation we use is very similar to the mathematical one. So the notation something like this. So we've got capital P and then in parentheses X, Y, Z. I mean, again, I get to cheat. You've taken Python. That looks like a function call, right? Similar idea, right? We take this function, just like in math, but we call this the formula is P. Well, I'm going to actually write it like this. P is the formula. X, Y, and Z are the variables. So all that means is we're free to choose X, Y, and Z to be whatever we want, and that will determine the truth value of the statement, right? So an example so P of X is the formula. X likes pretzels. Okay, so then the way we can, sort of evaluate this is we can use the notation P of Travis. And what this means is just like with a function in either the math or programming sense, you can come in, just feel free to sit down, is we're going to replace X with Travis, right? And then we're going to say, is this a true or false statement? Means Travis likes pretzels. So this is a true statement. Who here doesn't like pretzels? I just need someone who does. If there's no one here who doesn't like pretzels, then I'll just make something up. Is there anyone here who doesn't? Sure. Okay. What's your name?
Jordan.
Jordan?
Yep.
You don't like pretzels?
No.
Perfect. So that means Jordan likes pretzels is a false statement. Right? Because you could just ask us, do you like pretzels or not, right? And we get a true or false value. But we can plug anyone we'd like in here, right? And depending on what name we plug in, changes the answer. So also this is technically kind of a lie. I love pretzels. I have celiac disease, so they're poison to me. Literally, they are poison to me. I get food poisoning if I eat them. Oh God, they're so good. All right, Jordan, I love pretzels. See, this is me. I'm cheating. I'm also trying to learn people's names by plugging stuff in. Okay. So the reason for this is again showing that we can plug stuff in, right? I had an example on the quiz that was basically it was worded in a mathy way, right? Function evaluation. This is the same kind of idea. So another with multiple variables is x squared plus y is equal to 12. So that's the statement. So we can just plug numbers in and we get different truth values depending on that, right? So P of 2, 4 is, named by different colors. Look, it's late. I'm allowed to be a bumbling fool. So this is our x. That's our first value, right? We're going to plug it in for that. That's our second value. We're going to plug it in for y. So we're getting 2 squared plus 4. Is that a true statement or not? Right. Because 2 squared is 4 plus 4 is 12. So it's obviously false, right? What about 2, 8? Well, it's 2 squared plus 8 is 12. Is that true or false? It's true, right? Now, at this point, we're actually just evaluating the mathematical expression, right? We're doing 2 squared plus 8. What is that? It's 12. So that's a true statement. Okay. So an important thing to note about these sort of, formulas in the logical sense is we can plug anything we want into them, right? Like P of Travis and 4 is Travis squared plus 4 equals 12. Is that true or false? Who knows, right? Depends on context. So if we're talking programming, well, Python might interpret that as ASCII or something like that. I actually don't know what it would interpret as. It'd probably throw an error. But let's just say it interprets it as, one of these characters in ASCII, so it's a number, and then it adds it up, and it's just going to say false, right? But the point is true or false based on context, right? We need to know what is the context, right? Are we going to interpret this as a number in some way? Are we going to throw an error and just say that's invalid input? What are we going to do, right? We have to determine that. So a more mathematical example here is the following. So consider the formula x 20 bar y, which means x evenly divides y. So this is, I'm going to go on a bit of a side tangent here. I do that. I'm an eccentric math instructor. It's just how it is. So this right here, it's illustrative of something that comes up a lot in math. And that's that when students say they're bad at math, my experience is you're not. You're actually not as bad at math as you think you are. What it usually is that math has a lot of dependencies, right? Statement A needs you to understand statement B, which needs you to understand statement C, which needs you to understand D, and so on, right? So if at any point you miss one of those steps, then everything falls apart, right? You don't understand statement C, which means you can't understand B, which means you can't understand A. So I've asked you A, and you're like, I don't know what to do. But then when I sit down with you and I'm like, okay, let's figure out what you don't understand, and then you don't understand C, I explain it, and you're like, everything makes sense now. And that lets me say my extremely hot take, calculus is not that bad. Now, what I mean by that is in a traditional calculus course, there are 3 topics: limits, derivatives, integration. Now, of course, there's lots of techniques involved in there. I'm simplifying a little bit, but When students say they're bad at calculus, in my experience, they are not bad at calculus at all. They actually understand the calculus concepts very well. So like they understand what a limit is supposed to be theoretically. They understand what the derivative represents, that sort of thing. When I really grill them and I'm like, what are you struggling with? It's the algebra, right? Some piece along the way is missing. And that makes sense. Calculus depends on like 12 years of math or more, right? So if you're missing something there, you're hooped, right? You don't understand fractions. Okay, well then you don't understand rational functions. Now we're talking about rational functions and so on and so on, right? Like stuff like that. So it's not the calculus people that struggle with most of the time. Some people do struggle with the calculus. It's something along the way. And so that kind of gets to my point here is that we're doing that right now, right? So like, let's say you were working on an exercise and you saw this symbol and you're like, I don't know what to do. I don't know what to do with that. But then you just unpack it. You're like, okay, this means this. And what does it mean to evenly divide y? Well, this means we can find some r so that y is equal to that r times x. Like, let's just think of an example here. Let's unpack this. So 3 divides 6, this symbol means 3 divides 6, which means we're asking, can we fill in this blank? 6 is equal to blank times 3. Right, can we fill that in? Yeah, right, it's 2. This is kind of what I mean with my calculus rant, is that if you understand this part, then you can understand any question involving this. The problem comes in when you're like, this is the part I don't understand. When I talk to a student and they're like, I don't get it. This is the part that they just forgot. And then I explain this to them, I show them an example, like, oh, I get it now, and then they can do the question, right? So that's usually what I'm getting at is people aren't as bad at math as they think they are. It's just they're missing a piece, generally speaking. So have confidence is what I'm getting at, right? Be confident in math. But what the thing I'm getting at here is the context kind of matters, because let's change this. I mean, I think we all agree here, 3 evenly divides 6. So is 3 divides 2 true or false? Thoughts? Is that a true statement or a false statement?
False.
False? Does everyone think it's false?
No, true.
Yeah, so that's interesting, right? There's disagreement, and you're both right, right? That's the thing, is the context. I didn't give any context here. So context matters. In this specific case, are we allowing fractions or not? Right? That's really what it boils down to. So are we allowing fractions? So if we're not, then this is the divides definition for integers that we would know. So no, I'll say no fractions. That means 3 divides 2 is false because no integer satisfies. We've got 2 equals blank times 3, right? An integer doesn't go there to make it work, right? It's just, there's nothing that you can fit there. So this is a false statement. But if we allow fractions, then that changes the context. 3 divides 2 is true, since, well, same thing, we need to find a number that we can plug in there. Yeah, right? Exactly. 2 over 3 works, right? The 3's cancel out, now you got 2, it works, right? So this is what I mean, context, right? Are we talking about integers? Are we allowing fractions? Are we allowing people to go into this statement or just numbers, right? We have to be very explicit in what we're talking about. And it turns out that the intuition here, like if I ask 200 people this question, a bunch of them will say, no, this is a false statement, because when we in primary school, secondary school, whatever you learn, theory of integers, primes, that sort of thing, usually when you see the symbol, we're talking about integers only, right? We don't allow fractions, because if we allow fractions, the only situation where this is a false statement is if we do 0 equals blank times a number. Or sorry, other way around. Number equals blank times 0. Right? Because then we're saying, okay, 2 equals what times 0? That's impossible, right? Everything times 0 is 0, so that would be false. But literally every other situation is true, because every other number we can form a fraction with to cancel out. So if we allow fractions, this definition has no value or interest, because it's vacuously true. So when we restrict it to integers, now there's lots of situations where it's false, right? So 3 does not divide 2. 5 does not divide 7, because those are prime numbers. Stuff like that, right? Even for non-primes, like 6 does not divide 15, right? 2 integers. So the context determines whether or not a question is interesting, too. So I'm going to write this down just because it's kind of funny. When we want to explicitly write this context, it's actually called something when we need to specify this context. It is called the universe of discourse. And we'll never use that again. I just think it's funny that, you know, if you read lots of logic textbooks and philosophy textbooks, they'll say that a lot, like it's a normal thing to say. But it just, when you say it out loud, it just sounds kind of funny. The universe of discourse. But ultimately, it just means, in a mathematical sense, domain, right? What are we allowed to plug in, right? What are we considering to be variables? So in this example, integers, right? Not people, not fractions, not real numbers, integers. So, well, I mean, if it's not obvious from context, we can specify it. And it never hurts to specify it, even if it is obvious, because, I mean, it's one of those things where, I mean, you've probably had either a friend or an instructor where you're like, I don't get this. They're like, it's obvious, though. Yeah, obvious to you. You're the instructor, right? Like, I would never say that to a student, because they'd be like, Travis, how do you do this? And I'm like, isn't it obvious? It's like, yeah, I made the question. Of course it's obvious to me. It's not obvious to everyone. So it never hurts to be explicit and clear about what you want. Okay, so as it stands, we have the ability to write down simple logical statements, right? Travis likes cats. Okay, but that's not a very complicated sentence, right? What about things like Travis likes cats and Travis likes pretzels? That seems like a valid logical statement to make. I like cats. I like pretzels. So that whole statement is true, right? Because I like both. So we need to introduce the idea of logical operators. So how can we construct more complex statements? Or formulas. So we use what are called logical operators. And several of these you have already seen. A couple of them, probably not, because they're more for logical reasoning and deduction rather than for programming. But this is a math class, so we care about the logical reasoning part. So the first one what that's going to be is, well, if we have a statement, we can negate it, right? We can form its negative or flip it, basically, right? If something's true, we can just form the same statement that's false, or equivalent statement that's false. So if P is a formula, then not P, called the negation, or logical not, is denoted with sort of a backwards L. It's just our notation for it. So this thing here behaves pretty much how you would hope it would, right? If P is true, then not P is false, right? If P is true, then not P is false. And similarly, if P is false, then not P is true. So just as a quick example, I would say when it, in logic, the hardest part about using negation is just thinking, how do I say that? Like, how do I say the negative of that sentence in words? Because sometimes it's just not obvious. But you can always just use the symbol. Okay, so the sentence 6 is a prime number. Pop quiz, true or false?
False.
Yeah, right, and 6 is not a prime number. So this has negation. 6 is not a prime number. Normally you form the negative of a sentence by just putting a not in there. So this is a true statement. 6 is not a prime number, right? So we just flip the truth value of it. So like negative, right? Positive number, you negate it, it's a negative number. Same idea. So we can use the symbols. So if instead we wrote the negation symbol, 6 is prime, this is true because what we're saying is whatever's in these brackets, flip the symbol, right? So 6 is prime, that's false. This means flip it. Now it's true, right? So you can just write the symbol if you're like, how do I write this in words, right? Or how do I say that in words? But usually that just becomes a grammatical thing rather than a math thing. Like at that point, you know what you're supposed to do. You're just trying to find the words to write it down. So if you're struggling to find the words, symbol is fine. Okay, so now we can form the negation of a sentence. Great. That still doesn't let us do a whole lot, though. If we want to construct more complex phrases and sentences, then we're kind of going to need some other operators. So the next one is the logical AND operator. So if P and Q are formulas, and this is something, I mean, you're probably used to it from math, where we're generally pretty abstract when making definitions and that sort of thing. So that the structure of a math class is usually definition, theorem, then examples. So you'll write down the definition, you'll be like, the hell does that mean? That's just nonsense. And then we do some examples, and you're like, oh, okay, I get it now. So we're very abstract in the definition. So like P is any formula, Q is any formula. So I mean, these are basic examples, but like when we're talking about more complex definitions, it can help to just keep in your head what is an example, like just as we're going. So if P and Q are formulas, you just think, okay, Travis likes pretzels and Travis likes cats, right? You just think of something in your head to sort of unpack it. So anyway, if P and Q are formulas, then the formula P and Q, called the logical and, or disjunct or conjunction, which grade 5 conjunction and is a conjunction, so it makes sense. But we'll stick with logical and. And it's denoted like that. P upside down V Q. P and Q. So this P and Q is true. Well, if we think about it, if we're just thinking in terms of English rather than in terms of math, a statement like this is going to be true when both of these are true, right? Like Travis likes cats and Travis likes pretzels. Both of those are true, so the whole statement is true. Travis likes cats and Travis lives on the moon. It's a nonsense statement, right? The whole thing is nonsense because I included some nonsense, right? That's how we would think of that. So that's how we're going to say for the logical operators as well. Is true when both P and Q are true. So that makes sense. And just as an excuse to remind people about some mathematical notation, so the one I sort of just said, Travis likes cats. And Travis lives on the moon. This is a false statement because that second piece is false. So this is true. This is false. So as soon as we find a false statement in a logical and, we know we're done. We don't have to check the other one, right? Okay, what about this? True or false? Yeah, right? This first thing is true. Second thing is true. So that means the whole statement is true. But if we change that a little bit, true or false? False. Yeah, right? Because now it's less than rather than less than or equal to. Which, if you've been working with Python for several months, that's not hard. Or sorry, that's false. Maybe it is hard, and I'm lying. Right, and there's no reason that we can't just combine this, right? Like 2 + 3 = 5, and Travis likes cats, right? We can, they just have to be logical statements. They don't have to be only numbers or only words, right? You can mix and match them as you see fit. Okay, so that covers and. So all right, that's a good start, right? Like we're making progress towards being able to construct sentences in the English sense. So we're getting there. But in addition to and, we also have or. So we're going to talk about the logical or operator. Definition: if P and Q are formulas, then P or Q is called a logical or disjunction, and is denoted by P, and then it's V, P or Q. So this is a question I have to ask again from Python. Did you guys talk about exclusive OR? Good, okay. Then I can talk about it here. So there is actually two different definitions for OR, and we need to make sure that we're clear on them. And in terms of English, you might be like, what? No, there isn't. But there kind of is, depending on the context. So there's the idea of inclusive OR and exclusive OR. So I'm going to talk about inclusive OR because that's what the symbol means. That's the one we're going to be focusing on when we're talking about logic. So this refers to inclusive OR, namely P or Q is true if at least P or Q is true. And this isn't the logical OR, this is the English language OR. So P is true or Q is true, right? One of them is true. So what that means is if both of them are true, that's still fine, right? At least one of them has to be true. So if you had 6 different statements strung together here, one of them's true, we're done, right? The first one's true, we're already set. So looking at this, I'm going to do the annoying instructor thing, and I'm going to erase this, which means you have to write it again if you want. But same statement, Travis likes cats, or Travis lives on the moon. Is that a true statement or a false statement?
True.
Yeah, it's true. Because it doesn't matter that this is false, this is true. Same thing here. Is this true or is this false? Yeah, right? Well, I mean, same idea, right? It doesn't even matter what this one is. The first one's true, so that means the whole statement is true. Okay, but how about a more one that you'll actually have to maybe think about a little bit? When x is 2 and y is 0. Is this a true statement or a false statement? Right. Because, and everyone's quick about it because they see this first one, they plug the numbers in, it's true, and you don't even care, like, that's the thing, right? This looks like it's, I mean, these numbers are small, but it looks more annoying to calculate, right? So we check this one. Oh, it's true. We're done, right? So true doesn't matter. But that's false. So point is, the whole thing is true. So logical OR is true more often than not, right? Because all we need is one of the statements to be true. So the only time it's false is when both of them are false, right? Every other situation is going to be true. So now something to mention here, I said we're talking about inclusive OR, which means there is another type of OR. And that type of OR is actually, it can be important or useful for programming, but it is exceptionally important for hardware. Because hardware is built out of what are called logic gates. And there are 3 really important ones. Well, I guess 4. You have negation, logical not. You have and one of them is exclusive OR. When we're building logic gates, because it just turns out that lets us do more things than having inclusive OR when we're talking about building circuits and that sort of thing. So exclusive OR on the other hand, is true when exactly one of P or Q is true. So that means if P and Q are true, then it's false, right? We want exactly one of them. So there's no real consistency in this notation, so that's also why we don't focus on it. So sometimes denoted in symbols, it's the or with an underline. I think, don't quote me on this, but I think in circuits it's that. Maybe, I don't remember. I'm going to put a question mark there because I don't remember. In programming, it's XOR, exclusive OR. So if you haven't used it before, I'm pretty sure the Python syntax is literally that, so you can play around with it if you haven't used it. So it's sometimes useful if you want to consider both situations being true to be a failure case. So like if you, I don't know, you're doing like a class election, and you know your program at some point says both candidates won. That's fail state. That shouldn't happen, right? So you would use exclusive OR, and then you would catch that as, oh, what do I do when it fails, right? That's just a dumb, naive example. But there are lots of situations where exclusive OR is the correct choice to use. And determining when it's the correct case to use is hard. And when you use it, you can really simplify your conditionals. Because, I mean, you can sort of capture exclusive OR with ORs and ANDs, right? So if you just use an exclusive OR instead, then you cut down on your statements. But anyway, that's just an aside. So, okay, great. Now we can sort of form complex sentences, right? We can put ands and ors and nots in them to form like an actual English sentence. But when we're talking about math, we want to do more than just form sentences, right, out of old sentences. We want to be able to make arguments or logical jumps or conclusions, right? We want to be able to go from A to B, then to C, and then to D, right? That's an important part of math, which is deductive reasoning. Fun little tidbit. Math is not a science, which sounds weird because like when you're in school, it's STEM, right? Science, technology, engineering, mathematics. You think, okay, that's science. It's because everything uses it. Physics uses it. Chemistry uses it, yada, yada, yada. But in math, we don't form a hypothesis and then perform an experiment to test it. We do not use the scientific method at all. The way we argue in math is a lot more like a book report, where you have the text in front of you and you say, from this, I conclude this, which then lets me conclude this, which then lets me conclude this. There's a lot less ambiguity there because it is just a theorem formed from, I don't remember his name, Frankel or something like that. It's a German name. The guy who made the axioms of mathematics in like the 50s, he said, we got to formalize this. Zermelo and Frankel. They formed these axioms and then they build off of those, and that's where everything is formed from. So, you know, you can go from A to B to C to D in math very logically, whereas in a book report, it's kind of logical, but, you know, you're kind of at the whims of your teacher going, yeah, that makes sense, or no. So the point is, now we want to actually formalize that, right? We want to capture that. So this is another logical operator, which I'm pretty sure is not implemented in Python. It might be if you import a certain library. If P and Q are formulas, then P implies Q, or if P, then Q It's called the conditional. And is denoted sort of P arrow pointing Q. You might also see like a literal arrow. I'll accept, both are fine, right? It's either is fine. So like all the other ones, we have to determine when is this statement true and when is it false, right? We've got sort of a way of combining two statements. P can be either true or false. Q can be either true or false. So based on that, when is P implies Q true or false? So when is P implies Q true or false? And this is where it gets a little weird. Because if we think about it, we're trying to determine when if P then Q is a true statement, which is kind of weird, right? It's not in the traditional sense sort of a combination of two statements, but it also is. So let's think of this. If P is true and Q is true, then, well, I hope you'd agree that this whole statement is true, right? Let's think about it. If it's 6:52, then Travis is teaching. It is 6:52. Travis is teaching, and that sounds like a true statement, right? So I think when both of them involved are true, we can agree that's going to be a true statement, right? If P is true, then the true thing follows, right? That makes sense. Then P implies Q is true. Okay, but then if P is true and Q is false, well, let's think about it in terms of that example again. If it's 6:52, then Travis is not teaching. That's a lie. That's bullshit, right? Yeah, it's 6. Well, now I'm lying twice. If it's 6:53, then Travis is not teaching. I am teaching, right? So that second part is false. The first part is true, but that we'd agree that it has to be a false thing, right? You'd be like, but you are teaching. So what you just said is false. So in this case, we would say P implies Q is false. Okay, but we've now covered when P is true, but if P is false, then we still can choose Q to be true or false, and we have two more to worry about, right? So to find the others, consider the formula if x is less than 2, then x is less than 4. So true or false?
True.
Right? Yeah, like regardless of what we choose for x, this is a true statement, right? It's right? Of course, if x is less than 2, 2 is less than 4, so then that means x is also less than 4, right? That's obvious, just intuitively. So now let's use that fact. Let's choose some numbers here, and this is where it's going to seem weird when we write it down, but we do have two statements here, right? This is P, and this is Q. So let's let x be 1. Well, what do we get if 1 is less than 2, then 1 is less than 4? Again, we know this is true. We've already said it's a true statement, right? No matter what we choose for x. Well, this statement is true, and this statement is true. All right, cool, but we already knew that, right? We already agreed up here from another example that makes sense. But now, this is when things are a little weird. This statement now reads, if 3 is less than 2, then 3 is less than 4. But again, regardless of what we choose for x, we know this is a true statement. So right off the bat, that's true. Even though it looks weird. The reason why it looks weird is because we're essentially writing down nonsense, right? This is false. So in effect, it doesn't matter what follows after that, right? We started from nonsense, so it doesn't matter what happens. But it's still a true statement, right? If this thing that didn't happen, well, then anything can happen, right? Is basically what it's saying. And similarly, this is exactly the same kind of idea. If x is 5, if 5 is less than 2, then 5 is less than 4. This one is a little easier to unpack because it's like, well, 5 isn't less than 2, and 5 isn't less than 4. But it's still weird that we're calling that true. But again, it's because it doesn't make any sense to begin with. So it kind of doesn't matter. So this right here is more to convince you. We started with something that everyone was like, yeah, that's definitely true no matter what we plug in. And then we started plugging things in and people are like, wait, what? I wouldn't plug 3 into that because it doesn't make sense to plug 3 in. And you're right. When you plug 3 in, you get a false hypothesis or a false antecedent. So yeah, it doesn't make sense, but that doesn't change whether or not it's a true statement, right? In terms of truth values. Now let's unpack this in a different way that sort of explains this in another way, in a more relatable way, I think. So we can also think of this conditional as a promise. So another way, P implies Q is like a promise. And the best way to think about that is let's actually write it as an example with a promise. So suppose P is you win our bet. So I've made a bet and you won it. That's what P is. Q is I pay you. So either I do or I don't. True or false, right? I paid you, it's true. I did not pay you, it's false, right? You either won our bet or you did not win the bet. True or false? So P implies Q. What is that? If you win, then I pay you. So it's a promise, right? If you win, I'm telling you I'm gonna pay you, right? I'm good, I promise, right? Okay, so there's two situations. P is true. Or in other words, you won. Congrats, you won the bet. I don't know what we bet, but I'm not a gambling man, so it's easy to win. So if you won, there's still two cases we have to worry about. Q is true. In other words, I paid you. Well, in that case, I kept my promise, right? So, since I kept my promise, we're going to say the statement is true. Okay, well, the other alternative is I'm a jerk. And I didn't pay you. So in this case, I broke my promise. So because I broke my promise, we're going to say this is false, right? The promise has been broken. Okay, so we've handled the case when Q is true, or P is true, but this one we kind of already understood from the previous examples. So now we're going to get into the one where P is false, which is the weirder one. But when it's framed as a promise, it kind of makes more sense. P is false. You didn't win. Okay, well, there's still two cases. So in other words, we're saying P is false, and here we said P is true. So Q is true, or Q is false. But let's think about this. We made a bet. You didn't win. Does it matter what I do? Do I have to do anything? No, because you didn't win, right? I won. I don't have to pay you anything. But my intent to pay you, should you have won, did not change. Right? I still said I was going to pay you if you won. You didn't win, so it doesn't matter what happens now. I can still pay you to be nice because I feel bad, or I could do nothing. Either way, my promise is still kept, right? Because you didn't win, so I have nothing to do, right? So doesn't matter. Since you didn't win, my intent to pay you didn't change. I still intended to pay you. Or my promise to pay. Let's change that. My promise to pay you didn't change. I still promise to do that. So either way, I kept my promise. It's sort of a lazy way to keep a promise if the other person fails, but I mean, I still did it. So in that sense, the only time I have failed to keep my promise is if you won and I didn't pay you, right? That's the only time I have broken my promise. Every other time, here I kept my promise, obviously, because I paid you. Here I kept my promise on a technicality, right? But I mean, math is all about technicalities. But that sort of explains this, right? Like it's well, this first condition failed, so it kind of doesn't matter what happens. It just like it just kind of becomes vacuously true, right? Because this doesn't have an opportunity to follow up, but the intent or the promise was still there, right? If this were true, this promised to be true too, right? This was false, so, well, this still promised to be true. It didn't have to be because it was never tested, but it still promised that. So that's that weirdness of, you know, I guess this is sort of getting into like a philosophical or ethical discussion of what is a promise, right? If you didn't test me on it, did I keep it? Well, logically, yes, you did.
Travis.
Yep.
I didn't understand anything you did there because you said if P implies Q, if P is false, then it doesn't matter. Whatever happens is false, right?
Yeah.
That was what
No. Whatever happens is true.
Really?
Yes.
Wait. If P is true and Q is false, then P imply Q is false.
Yes, that's this one right here.
Okay.
If P is true and Q is false, then P implies Q is false. But if P is false to begin with,
Okay.
then what I'm saying is my promise didn't change. I still promised, and by a technicality, kept that promise. The only situation in which I don't keep it is where I explicitly don't keep it, right? Now, this is all, so to be clear, this is all just the explanation for how this came to be and why this is the truth value for this. We're going to talk about truth tables next class, and then the reason why doesn't matter very much anymore. What you need to know is just the truth values. So this is just, look, I was a young mathematician once. Now I'm old at 36 years old. But I remember the first time when this and the one I'm about to write down were first presented to me. I was like, this is so weird and confusing. When you start seeing more examples of like proofs or theorems of if this then that, then the reason for this starts to make more sense. Like you'll just start seeing enough examples of why this sort of definition ends up making sense. When I try to explain it in a bunch of different ways, it still seems weird because a lot of people will look at this and they're like, how can this be true if the first thing is false, right? But that's not the right framing, because what you're, so this is actually an important thing about logic, and this is where it's weird. There are two concepts in logic, in deductive reasoning. There is my logical argument valid, and is my logical argument sound? And they do not have to both be true. You can have a valid logical argument that does not make any sense. So a valid logical argument, if you write it down on this and you break it down into P's and Q's and write down the logical formulas, it's valid. It's correct. But then when you think about it in context, it's nonsense because you started with nonsense, and that's kind of what this is, right? If you were trying to argue from this, false implies true, that's logically true. I wouldn't recommend building a logical argument off of that, though. So what a logical argument being sound is that you start from true assumptions, which would mean that you're never in this situation. And often in math, we are never in this situation. So we don't actually have to worry about this. But this truth table matters when we talk about, well, I'm cutting them out of this course, so it matters less. But proof techniques, because one of the important proof techniques is proof by contradiction. And the existence of this truth table matters for that proof technique. So an example of an argument that is logical but not sound is all golden toasters are time travel devices. I am a time travel device, therefore I'm a golden toaster. It sounds like bullshit, right? Because it is. It's not a sound argument. If you write down the logical steps, it's true. It's a valid argument. Like A follows from B in that, but it's not sound at all. I sound like a moron saying that because that's true. I am. So this is getting into the nitty gritty of like whether or not an argument is valid versus sound. We don't care about that too much because in math, other than for specific proof techniques, we really are concerned with this case, right? We are starting from a true hypothesis. What happens then? If we start from a false hypothesis, well, the point is logically you can argue whatever you want. So don't start from it because it's not a sound argument. It's valid, but it's not sound. Okay, so the final one is related, and that is biconditional. Suppose P and Q are formulas, which is not a surprise. Then P, if and only if Q is called the biconditional, and is denoted P sort of double arrow Q. Makes sense that that's the notation we would use. The other one is the conditional and it points one direction, biconditional, bidirectional, points both ways, right? Makes sense. So this is true when P and Q have the same truth value. So if P is true and Q is true, then this statement is true. If Q is false and P is false, then this statement is true. So it's when they match. So if they're so you can essentially think of for truth table purposes when we're talking about that and algebra, this thing here is basically checking if they're the same. Sounds an awful lot like equality, right? And that's important, right? This is checking essentially if two things are the same, right? Either P is true means Q is true, or P is false means Q is false. So they have the same truth values. Okay, great. So now we have, not only can we construct complex sentences, we can sort of argue things. We could do A implies B implies C, right? If A, then B. If B, then C, right? So we can reason now with these. And that means that we can construct complex compound sentences, right? So we can combine these in all kinds of ways. We can combine in all kinds of ways to create compound sentences. So that means you can just slap them together in whatever order you want, right? So you could say A implies B, or hold on, I want to make sure I write down the same thing. C and not B, right? Just write down random stuff together, right? This is a compound of, now it's four things, but still fine, right? If A, then B or C and not D. Right? Like we can just read that out as words. But here's it's a pop quiz for math. I hate this kind of crap that you see on Facebook or whatever. What do I do first? What's the answer to this? 14, yeah. So how did we know to do that? Because we have an agreed upon order of operations, right? Yeah, we know BEDMAS or PEMDAS, right? So we know we do multiplication first, right? So the same is true for these logical operators. We have an agreed upon order, and don't quote me on this, but I'm pretty sure programming languages universally also agree on this order. Again, please don't check it, because I'm sure you could find some obscure thing that's like, well, this doesn't agree, and okay, fine. We agree on the order. So first is negation, then and, then or, then conditional, and then biconditional. And I for programming, this doesn't matter as much. I don't know where XOR falls in. Somewhere around here. Either before or after or. You'd have to check documentation. In terms of logical operators, XOR is just a combination of or and. So we don't put it anywhere. But in terms of logic gates, I don't know where it falls. But the point is, that means we have an agreed upon order for this. This is A is the last thing we do, or the implies is the last thing we do. Before that, we need B, or. Well, to find this, we need C and to find that, we need to find not B. So what this is saying is, first, figure out the truth value of not B, whatever that is. Once you have that, use it to find the truth value of C and not D. Then once you have that, do B or blah. And then once you have that, you can figure out the whole thing. Now, one thing to note here, and this is why I say that the stupid things on Facebook that like everyone's arguing in the comments over is like, what's the answer to this question? Do you divide this like this or that? Use brackets. And then nobody is wondering, right? With an asterisk, it's really hard to overuse brackets because they just make it extremely explicit what order you want things done in, even if it matches the order of operations. So like here, this matches the order of operations as this, but this is more clear what I'm doing, right? Because clearly I do brackets first, no matter what. So I got to do this. Okay, once I know that, now I can unravel the brackets, right? And I'm sure in your experience programming, that has been true too, where just wrapping your conditionals in brackets is just helpful for keeping track of things, right? Like just, even if you know the order of operations for ands and ors and stuff like that, and nots, it's still nice to just keep that clear, right? So it's, I think it's hard to overuse brackets. Most mistakes that students make in algebra is they just didn't include brackets or misread the brackets, right? So include brackets. Okay, so that's where I want to stop for today. Next class, we're going to talk about truth tables, which at the end of the day, like you look at this and you're like, okay, this is a lot. First of all, because now I have to remember like 3 different ways of keeping track of this information. No, you don't. There is one very concise way to organize all of this information, and you can use it for computations. It is called a truth table. So like it looks like this. So we've got P and Q. So P can be true or false. If P is true, Q can be true or false. If it's false, it can be true or false. And then, you know, P and Q, P and Q, P and Q, P and Q, right? So now you have the information right in front of you. If you're like, okay, my P is false and my Q is true, what's the result of my expression? Oh, it's just right there. Right? I don't have to remember, you know, the logic for why it's that. I just look at this. And the reason why this is helpful also is, well, true or false. What does that look like? What else does that match in computing? Yeah, binary. So you can encode truth tables in binary, and this helps you understand how bitwise operators work. I don't know if you've really worked with bitwise operators in Python. I don't even know. I'm sure it does, but it's not common to use those. If you're a C programmer or have experience with C, you definitely know bitwise operators. And this is exactly it, right? Bitwise AND returns 1 when their inputs are both 1. So anyway, that's the value of these truth tables, is you can encode them in binary, and that's very helpful. And they match the operators in C for binary, and they also match the logic gates that computers use fundamentally. So there is a point to this. It's not just me writing math for math's sake, even though sometimes it feels like that. Anyway, that's all. So have a good evening. Nice way to finish the evening with an extremely energizing lecture in math, right? You know,
Great.
I'm sure it's going to be really exciting throughout the term.